Using threat analysis on the Kaspersky Threat Intelligence Portal. In this video, we will demonstrate how to conduct a comprehensive file analysis using the Threat Analysis section of the Threat Intelligence Portal. Let's imagine that a CM system rule was triggered by suspicious arguments used to start a PowerShell.exe process. SOC analysts requested the executable file that initiated this suspicious activity so that they could conduct a detailed analysis. The Threat Analysis section provides three technologies: sandbox, attribution, similarity. Let's upload the suspicious file and configure the analysis settings for sandbox. File execution environment. It's best to specify the runtime environment where the suspicious file was run. If you don't know which specific operating system the file is intended for, select Auto. File execution time, sec. Amount of time to run the file in the sandbox. You're advised to specify a fairly large execution time because some samples require more time to start their activity. Many samples use an anti-emulation technique based on delayed execution. Internet access option. Here you can either specify your own country, such as the country in which the sample was detected, or you can see if the sample behavior changes for different countries. The tar pit option is also available. This option is used when the internet is unavailable or if the suspicious file must not have internet access. Change file name and extension to. It's best to leave the original file name instead of sample.exe or malware.exe because some samples verify their name as part of their anti-analysis techniques. Document password. If you are analyzing a password-protected document, enter the password. Command line parameters. If the suspicious file was executed with additional parameters, enter them in this field. Let's save these settings and move on to configure the attribution settings. Unpack. This option enables attribution technology to analyze objects that are contained in the original file if it is a packed file. Reset similarity thresholds. Attribution considers a sample to be similar to a malicious actor's file if the number of common genotypes or strings is equal to or exceeds the set threshold value. A threshold is specified for each sample in our database. If you do not enable this option, attribution will return fewer results, but better matches. For example, if attribution returns no results with the checkbox cleared, you can submit the file to attribution again, but this time enable this option to ignore the threshold. You do not need to configure the settings for similarity. Now we can submit the file for analysis. For each technology, you can see the task and its status. Sandbox results will take longer to process than attribution or similarity because the sample is executed in real time. Open the attribution results by clicking the attribution link under Details. Attribution technology helps establish a link between a new attack and known APT threats. This could be a specific threat actor, malicious campaign, or malware. Attribution extracts the genotypes from a file submitted for analysis and searches for similarities with already known samples of APT threats. Genotypes are the unique fragments of code extracted from a malicious sample that are not encountered in any clean file, which means that they are specific to this particular malicious object and therefore help identify the attribution match percentage. In our case, attribution technology did not find similarities with any known APT groups or malware. Now let's see if we have found any similar files using similarity technology. Similarity technology searches for malicious files that are similar to the suspicious object that we are analyzing. To search for similar files, the technology uses machine learning algorithms to extract individual fragments of the submitted file and then calculates special hashes to search for recurring fragments in malicious files. Please note that attribution and similarity technologies use different algorithms to detect similarities between files. Therefore, similar samples from attribution may differ from those obtained from similarity. The similarity report provides information about the similar files that were found, including their status, detection name, and confidence, degree of trust in their similarity. This section can display up to 100 files. In our case, we found 5 similar files. Based on the verdicts for the similar files, we can conclude that our suspicious file most likely belongs to the same malware family. From here, we can also proceed to the threat lookup section to quickly get additional information about a file and see its associations with other objects. Information about similar files may be used for incident response purposes to conduct a broader search for malicious file variations and help contain APT threats. This information helps optimize protection by considering various modifications of a malicious object. If the incident response team has the MD5 hashes of similar files, it can conduct an IOC scan in telemetry to find other files within the infrastructure and thereby obtain information about other infected hosts. You can also download samples from publicly available file collections such as VirusTotal. Let's assume that we obtained the hashes of several similar files and then detected these files in our infrastructure. To get more detail about the purpose of these files, we can submit our detected files for analysis with all 3 technologies. While we wait for those results, we can view the analysis results for the file that we previously submitted to the sandbox. Sandbox collects artifacts during the time period that we specified. After an analysis, Sandbox displays a summary report that includes the verdict, suspicious activity, and network connections. In addition to classification and triggered verdicts, Sandbox displays a sample execution graph, execution map, that illustrates the actions of the file. We can see that the executed file contacted an internet resource with an automatically generated DNS name. Let's copy the domain name and check it in Threat Lookup. According to information from Threat Lookup, the resource is malicious and was already observed in APT attacks. As we can see, many malicious files interact with this resource, thereby confirming its reputation. This resource can be added as an IOC, and you can track files that attempt to communicate with it. The graph shows us that the following occurred during file execution. PowerShell execution policy bypass, PowerShell script execution from a public directory, network connection over HTTPS from a PowerShell process. The file behavior is automatically classified according to the MITRE attack matrix. Its corresponding tactics and techniques are identified. At this stage, we know that the file starts a PowerShell script that collects system info and forwards this collected data to a malicious resource. Now let's examine the artifacts collected by the sandbox. You can see all the collected system events. Modules loaded into a process, loaded PE images, operations with files, file operations, operations with the registry, registry operations, process creation and termination events, process operations, operations with synchronization objects, events, mutexes, semaphores, synchronization operations. Let's view the available information on the extracted files. Files contained within the analyzed file, packed object content, files transferred over the network, transferred files, For more details about these files, see the Network Activities section. Files that were modified and saved to the system, dropped files. Each file can be downloaded for additional analysis. Files are saved in a password-protected archive with the password infected. For example, you can download a PowerShell script and view its contents. As we can see, the PowerShell script is encoded. The sandbox also showed that the script collects system info. We can view information about the following network connections: HTTP, HTTPS requests, URL, method, response code. This is the known domain api.ipfi.org that is used to identify a public IP address. Some malicious applications use it to determine the geographic location of their victim. We can also view other network activities such as the following: IP, TCP, UDP, TLS, and other sessions. To download a detailed file execution report that includes the main events and when API calls, click Expert Results at the top and then select Debug Report. You can also download a PCAP file and import it into Wireshark for additional analysis. In addition to file classification, the sandbox is especially useful during the incident response process because it allows you to accurately determine the intent of a file and predict its potential impact. Now let's view the results of the analysis of those 5 similar files. We previously submitted 5 similar files for analysis. Let's see if an attribution to known APT attacks was detected. We can see that 2 files have been attributed to the APT group known as Muddy Water. For example, attribution technology found that the 3rd file has a 99% match similarity with the APT group Muddy Water and shows the files that were used as the basis for this conclusion. There are a total of 2 matched files. One is a 99% match and the other is only 3%. We can immediately check the file hash in threat lookup. Below, we can view the hashes of the genotypes that matched the Muddy Water genotypes from our database. Attribution also searches for matches based on strings, such as keywords, file paths, function names, and individual strings. If the system attributed a file to a threat actor whose profile is listed in the Kaspersky Threat Intelligence Portal database, you can click on this actor for additional information. Here we can view threat actor reports, from which we can export additional IOCs, Yara rules, and Sigma rules if they are available. A profile card provides the following detailed information about a threat actor: brief description, software used, exploited vulnerabilities, detailed MITRE techniques and tactics. By knowing which APT group is behind an attack, the incident response team can effectively investigate and respond to an incident and contain the threat. Using threat actor data obtained from TIP, analysts can determine the objectives and motives of the APT group, identify the potential attack vector, apply Sigma rules that detect techniques employed by the APT group, import IOCs associated with the APT group. Thanks to the set of technologies demonstrated here, we successfully conducted a comprehensive analysis that allowed us to identify the malware's behavior and objectives, identify its various modifications, and establish its association with a known APT group and its techniques and tactics. In our specific example, the presented technologies clearly complement each other. It is their synergy that allows us to identify a sophisticated threat much faster than if we were to conduct an analysis using only one of these technologies.